Hi, I'm Bobby Goodall from Cosmodyne, and I'm going to give you a very basic walkthrough of our GFED air separation plant. Okay. The process all begins with our air compressor. For this particular plant, we have a two-stage oil-cooled air compressor, which takes atmospheric air and recycled air from our air separation unit and compresses it to about between 125 and 140 psi. This is the heart of the whole operation. The compressed air gets fed through to a chiller unit. We'll talk more about that at the moment. But let me begin with a little bit of detail about the air compressor itself. So our air compression process begins with the compressor pulling ambient air into our suction filter. All right, inside here we've got a pleated paper filter element. This particular line is coming back from our compressor. It's recycled air that's being recompressed again. But if you look on the other side of this filter housing, you'll see there's an opening, and it's just pulling ambient air down through this valve, which is a control valve, which is controlling how much air the compressor is pulling in, down into the screw itself. This is a two-stage oil-flooded screw compressor. Okay, so our air is pulled down into our screw, and the action of the screw forces the air into a smaller and smaller space, which causes compression. Okay, the compressed air is discharged on the other side. We'll get a view of that side in a moment. But just while we're here, you can see the motor of the compressor driving the screw down here. And you can also see two heat exchangers, one on this side and one on this side. Now, the compression of air obviously causes a lot of heating of that air. We're compressing air from ambient atmospheric pressure to around 10 bar at 140 psi, and the heat of compression is considerable. So before we send our compressed air to our chiller or our reefer unit, we need to cool that air as much as possible. So we have a large fan, which you can't see from your angle, but there's a large fan which will pull air through this heat exchanger and another heat exchanger here. So if you look at the base of this vessel, which is our oil separator, you'll see the inlet line for the compressed air. Our compressed air moves up through the separator and out through this valve and into our heat exchanger before dropping down where our condensed moisture is eliminated and then flowing onto our reefer unit. So this oil separator is essential to remove the oil, the lubricating oil from the airstream, sends it up through the heat exchanger and returns it via these two oil filters, returns it back to the sump of the screw compressor. Okay. The reason we don't want any oil in our airstream, obviously we don't want our oil levels inside our screw being depleted over time, but critically we do not want any hydrocarbons making their way through to the air separation process. As you may know, any hydrocarbons that accumulate inside our liquid oxygen inside the columns can cause spontaneous combustion, which obviously is disastrous. So, very, very important piece of equipment, the oil separator. On the back end of the compressor, you'll find our discharge line with our high pressure airstream, which moves through our reefer unit. We'll go through to our reefer unit now and discuss the components there. Right, so this is our chiller unit or our reefer unit, which is basically a large refrigeration system. It's very similar to the system that you would find in an air conditioner. And this entire unit, the entire chiller skid, is here really for only one purpose, and that is to cool our process air down to a suitable temperature where we can condense liquid from the process air. We do not want liquid moving through to our air separation process because at the cryogenic temperatures inside the column and inside the heat exchangers, we will freeze that liquid. All right, so it's very important that we get all liquid out of our airstream, and this is the second step after the initial coalescing of water in the compressor. This is the second step for knocking out water. So basically, it's a usual refrigeration system we use. For this system, we're using our refrigerant is R407C. We have a compressor which sucks in our Freon gas, compresses it into a high pressure gas. The high pressure gas flows through into a condenser unit, which is basically a heat exchanger. The heat exchanger has 4 fans which are pulling ambient air through. And in that process, inside the heat exchanger, our high pressure freon is cooled down to a point where it begins to condense into high pressure liquid freon. Okay. We take this liquid freon and we move it through what we call a metering device or a expansion valve, where we have a pressure drop, and as that liquid expands through that metering device, it comes into thermal contact with our process air on the other side of the heat exchanging fins, and it begins to boil. And the boiling of that freon absorbs a huge amount of heat from our process air, and in doing so, our process air is cooled down. So if you look at all the piping involved in this system, most of the piping and equipment you're looking at is freon related. The only piping that's involving our process air stream is this line coming in here, and you can see it come into the base of the evaporator and out of the evaporator and into this large cylinder here. You can see the air line will come into the base of this large cylinder, and this is our coalescer. Our coalescer basically is a vessel for coalescing or condensing moisture out of our process air stream. So the process air that we have chilled should ideally be about 3 to 7 degrees Celsius, and that's a perfect temperature for condensing liquid out. We have 2 automatic drains here. They have built-in level sensors, and as the level of liquid begins to rise in the coalescer, those valves will open and close accordingly to maintain the level of liquid in the coalescer. The liquid is just purged to atmosphere outside. So our air stream that comes out of our coalescer is now ready to be sent to our purification unit on our ASU. It's had most of the moisture knocked out of it, and by the time it comes through the coalescer, we're probably looking at air that's about 7 or 8 degrees Celsius, ideally, ready for purification. Another quick note on our chiller. We have 3 basic controls on this chiller. Obviously, the chiller is just, the compressor is pumping away at full capacity. The fans are running, but we need a way to control the temperature of our air according to the ambient conditions of the particular day and according to how much load we have on our plant, how much air our plant is actually using. Obviously, if we have a small flow of air going to the plant, the chiller has a very small load, has a small heat load on it. So we may find that our chiller will begin to cool the air too much. And if we get air cooling too much, we will get moisture freezing in our evaporator, and we don't want that because we will block up the process. So we have 3 basic controls. One is our hot gas bypass, one is our unloader, and one is our fan control. Our hot gas bypass is basically, our hot gas bypass and our unloader are both controlling our suction pressure. They are regulating our suction pressure, and in doing so, they are regulating our suction temperature. Okay. So if our suction pressure begins to get too low and our temperature begins to get too low, the hot gas bypass or the unloader, they have a pressure switch inside, and when that pressure gets to a certain point, the contacts will close in that switch. The hot gas bypass will bypass the condenser unit. So we will send hot compressed gas directly from the compressor to our expansion valve. All right, therefore, we are bypassing our condensing. We will raise the pressure inside the suction line. We'll raise the temperature inside the suction line. The unloader does a similar thing. It raises the suction pressure, but it does this by activating a solenoid coil on top of the cylinder head here. And what that does is open the valve at the top of that cylinder. Our compressor has 2 pistons running full time. When the unloader is engaged, when our suction pressure drops enough for the unloader to be engaged, this solenoid will open the valve at the top of that cylinder so that our 1 piston has no compression. So basically what it is, it's a capacity regulator. It will reduce the capacity of this compressor by 50%. Only 1 piston will be compressing. And if we reduce the capacity of our compressor, then we are raising the suction pressure because we are not pulling as much liquid through the suction line. Sorry, pulling as much gas through the suction line. All right. Our third control is a control that's related to our discharge pressure, the pressure on the discharge side of the compressor. And in our condensing unit, we have 4 fans. 2 of those fans are running full time. If our discharge pressure gets to a certain point, the set point being set by these screws here, if the discharge pressure gets to a certain point, the contacts will close in this switch and the additional 2 fans will switch on. What that will do means more cooling, means more condensing, means a drop in our discharge pressure. All right, so that's how our temperature is regulated in this system. So again, basic components: a compressor compressing our Freon gas into high pressure gas, moving through our condenser, becoming liquefied, moving through to our metering device, which is expanding our liquid, regulating a flow of expanded liquid into our evaporator. And our evaporator is the second heat exchanger where Freon, bubbling Freon, boiling Freon, comes into thermal contact with our airstream and cools our airstream. That Freon is being vaporized as it moves through the evaporator, and it makes its way back into a receiver where any remaining liquid can boil off before the remaining gas is returned to the compressor. Why we have that receiver, we call it the suction receiver. We have that because we cannot compress a liquid, and we want to be 100% sure that no liquid returns to the suction line. So any liquid that does make its way through the evaporator will fall down into the suction accumulator and will harmlessly boil off. Okay. This system is set up so that the evaporator has about 8 degrees of superheat, meaning that the Freon that is boiling inside the evaporator, by the time it makes its way through, it becomes a vapor, and the vapor leaves the evaporator, should be about 8 degrees higher than the boiling point or saturation temperature of the Freon. Okay, and that superheat is a safety margin that will make sure that we don't have any liquid coming back to our compressor. So these are our 3 controls, and then we have some safety switches. We have a high pressure switch, a low pressure switch, and a low pressure oil switch. If for some reason our oil pressure drops, this oil pressure switch will trip the compressor, trip the chiller compressor. And likewise, if the discharge pressure gets too high, we have a high pressure switch which will trip the compressor. If our suction pressure gets too low, we have a low pressure switch which will trip this compressor as well. We also have a pump down mode, which is a maintenance mode. It's not normally used during the running of the plant and the running of the chiller generally. And what our pump down mode will do, it closes a solenoid valve in our liquid line, and it ensures that all the liquid Freon, all the Freon in the system returns to the accumulator. So it's a maintenance procedure. If we're finding that too much of our oil has made its way out of the discharge and into the system, then we can do pump down, which will help to return oil to the compressor. Okay. We do have an oil separator here so that our discharge stream moves through this oil separator, and most of the oil should make its way back through this line and into the sump of the compressor here. But you do get tiny amounts of oil that will make its way into the Freon stream and might get trapped inside the condenser, and pump down mode is a good way of bringing that back. So if you're finding repeated trips on low oil pressure, pump down mode a couple of times may help to bring your oil level back and eliminate that trip. Okay, so this is our hot gas bypass valve, and this solenoid on the valve, the solenoid you can see here, is activated by the hot gas bypass switch. When our suction pressure drops, this solenoid will be activated and open up this valve, and this will allow hot gas directly from our compressor discharge to make its way through to our thermal expansion valve. The valve is a self-regulating valve. You can see the small line on the downstream side. So it has a reference pressure on the downstream side. And apart from being either on or off, open or closed by the solenoid, the valve actually regulates the flow of hot gas according to the downstream pressure. So as the downstream pressure rises, the valve will allow less and less hot gas through. Okay, in this shot you can see we have a liquid line coming from our condenser. There's a sight glass here where you should be able to see the liquid freon. Sight glass should normally be fairly full of freon. You might see the odd bubble. And the liquid will be coming through our thermal expansion valve. You can see the tag here. And evaporating, boiling off into our, expanding and boiling off into our evaporator and returning as gas through this line to the suction accumulator. This expansion valve has a reference pressure as well from the low pressure side. So it also has a temperature reference from the low pressure side. So it is a regulating or metering valve which will regulate the flow of liquid freon through that orifice depending on the pressure downstream and the pressure and temperature downstream.